In this lab, we will measure the temperature change and the magnitude of the rate of temperature change during evaporation for a series of homologous alcohols and polar organic compounds to explore the relative strengths of intermolecular forces. Recall that evaporation is essentially the phase change from liquid state to gaseous state. Unlike the process of boiling, which involves the formation of vapor bubbles from within the liquid, evaporation is a surface phenomenon where particles escape from the liquid surface to the surrounding gaseous environment. The rate at which this process occurs is dependent on the strength of the forces, that is, the intermolecular forces holding the particles in the liquid state. Evaporation is an endothermic process. Energy is required to break the intermolecular forces, and this energy is transferred from the surroundings as heat. This means that we can monitor the rate of evaporation by measuring the rate of decrease in temperature of the surroundings. This approach is not practical with an entire beaker of a liquid since the temperature change is too small due to the large amount of liquid in the beaker compared to the evaporation surface area. But if we allow the evaporation to occur from the surface of a filter paper saturated in the liquid, then a drop in temperature of the surroundings should be easily measured. Although the experimental approach in this lab is simple, the resulting data provides a clear correlation between the types and strengths of intermolecular forces and the temperature change and magnitude of the rate of temperature change during evaporation. We will apply this approach to a homologous series of alcohols, from methanol to butanol, and a set of polar organic compounds, diethyl ether, methyl acetate, and butanal. A uniform piece of filter paper is secured to the bottom part of a temperature sensor. It is worth mentioning that the temperature is only measured around this region of the sensor. The temperature sensor is connected to a LabQuest 2 data logger. This allows for continuous temperature measurements over a period of time, which are plotted as a displayed graph. The temperature sensor is lowered into the liquid organic compound until the temperature is stabilized and the filter paper becomes saturated with the liquid. The time data collection is started so as to establish a temperature baseline. When the temperature sensor is removed from the liquid, as seen in the diagram, evaporation from the liquid-saturated filter paper begins and the temperature drops. Our goal will be to measure the rate of temperature decrease and the total temperature change for each of the homologous alcohols and polar organic compounds. Scott turns on the LabQuest 2 and inserts the connecting wire from the temperature sensor into the channel port. The LabQuest 2 displays a live reading of temperature. As Scott holds the tip of the sensor, we see the temperature increase from about 21 degrees Celsius to 30 degrees Celsius. Scott also highlights the various features available from the File button in the menu bar, such as Open, Save, Delete, and Export a file. The Sensor button allows the user to set specific parameters and calibrate the different sensors. In this experiment, the only adjustment required is done by clicking the Mode tab and changing the duration of the run to 120 seconds. Scott secures a piece of filter paper onto the tip of the temperature sensor using a small elastic. Notice that all the pieces of filter paper are of uniform size. temperature sensor with the filter paper is inserted into the bottle containing methanol so that the filter paper is completely submerged in the liquid. Once the temperature is stabilized, the start button is tapped and the collection of temperature versus time data is initiated. Data is collected for about 20 to 30 seconds to ensure an accurate determination of the initial temperature. Then the methanol bottle is lowered and the methanol saturated filter paper is now exposed to the surrounding air. The LabQuest 2 screen shows that the lowering of the methanol bottle coincides with the drop in temperature. Let us revisit these initial stages of the experiment as we look directly at the LabQuest screen. The temperature is stabilized while the filter paper and the temperature sensor are submerged in the liquid. The start button is tapped and the data associated with the initial temperature is collected. At this point, the methanol bottle is lowered and the methanol saturated filter paper is now exposed to the surrounding air. This coincides with a dramatic drop in temperature. The temperature continues to decrease until a minimum temperature of below 8 degrees Celsius is reached. This process is repeated for the other 3 alcohols and the polar organic compounds. The maximum change in temperature for each run can be determined by clicking Analyze from the top menu, Statistics, and then Temperature. The relevant data can be found in the right-hand side panel. By subtracting the initial maximum temperature from the final minimum temperature, the change in temperature is obtained. In this case, a difference of negative 14.8 degrees Celsius is observed. The negative sign shows that there is a drop in temperature. The magnitude of the initial rate of temperature change is also determined. The first 5 to 10 seconds of the temperature drop is highlighted. The Analyze, Curve Fit, and Temperature buttons are then selected. We then choose a linear fit. The parameter that we're interested in is the slope, or the M value, as this will give us the rate of temperature change in units of degrees Celsius per time. We will take the absolute value of the rate, as the negative sign only refers to the fact that the temperature is dropping. In this case, the recorded value is 0.597 degrees Celsius per second. This process is repeated for all the liquid samples. After watching this video, you will have access to a complete data set for both groups of compounds. Before we get to this, however, it is interesting to step back and look for patterns in the data set. All the runs can be seen in this unlabeled graph from the LabQuest 2. To help you see some of the trends, the data has been replotted using Excel. In Figure 1, we see temperature plotted as a function of time for the homologous series of alcohols. It should be clear that the lower the molar mass of the alcohol, the greater the corresponding overall change in temperature. Further, an inspection of the first few seconds of temperature drop shows us that the lower the molar mass of the alcohol, the greater the initial rates of temperature change. In Figure 2, diethyl ether, followed by methyl acetate, has the greatest overall change in temperature, and also the greatest initial rate of temperature change. We do see in this case, however, that after reaching a certain minimum, the temperature starts to climb back to room temperature. A possible explanation for this is that the liquid sample has all evaporated by this point. It is likely that the maximum change in temperature is, therefore, not achieved for these examples. For this reason, it is generally believed that the initial rate of temperature change is a better reflection of the relative strengths of the intermolecular forces. As mentioned earlier, after watching this video, you will be provided with a dataset from your Moodle lab course. The dataset will look something like what is shown in this diagram, but please use your own data and not what is in this diagram. Your task will be to use Excel to generate a total of 4 graphs. Table 1 shows typical data for the homologous alcohol series. Using this table, you will need to make Excel plots of temperature change and rate of temperature change as a function of molar mass. Table 2 shows typical data for the polar organic compounds. Using this table, you will need to make Excel plots of temperature change and rate of temperature change as a function of dipole moment.